right, so there are two crucial limits that we're going to define today that involve sign. And then we'll pretty much be done defining limits. So we spent 2-1 A and B and 2-2 A and B all talking about limits, different kinds, one-sided limits, limits involving infinity. Today is limits involving sign. We're going to define two of them, and from those two, you should be able to do all the problems that you need to do involving sign. So it's going to go by definition. The limits we're going to talk about today are the limit as x approaches 0 of the sign of the function sine of x over x. And we're also going to talk about the limit as x approaches plus or minus infinity of sine of x over x. The values of these two limits are something you have to memorize. I will show you how to prove them. You won't have to recreate those proofs, you just sort of have to understand them. It's not like geometry where it's like you have to do these proofs. But I'm going to show you the answers, and usually you guys will believe me that I'm just telling you the truth, but I am going to show you why those answers are true. But I want you to make a conjecture. Can you grab out your calculator, and in radian mode, can you graph sine of x over x for me a minute and just take a look at what that graph looks like? So our hypothesis is that the value of this is 1. And if you're asked to prove it, the proof kind of comes in two ways. Like, well, I can prove it because I checked the limit as x approached 0 minus of sine of x over x, and it equaled 1. And we checked the limit as x approached 0 plus of sine of x over x, and it equaled 1. So even though there's a hole there, the limit is still 1. That's something you're going to need to memorize. Furthermore, a corollary to this, a corollary is like a addendum. What is the trouble? All right, a corollary. What if you're... has to pair a minute. All right, the limit as x approaches 0 of sine of ax. So what if you have a coefficient now in front? Is the limit value still 1? And the corollary is no. The limit value is now a. If you're going to insert a coefficient into x, then it's going to affect the limit. Okay, I'm going to pause it. Let's experimented with changing the a on our calculators, and we've seen that it does in fact change the peak. All right, now we need to talk about positive and negative infinity. What's the limit of this graph, this function, if you're on either side? Okay, we were just looking at the middle at 0, 0, figuring out where at the origin where it was. What about on the outside edges of this function? So you're going to go back to your calculator and make your window in the x direction larger. So go ahead and on your window, right now it should be set to negative 2 pi to 2 pi. Try something like negative 10 pi to 10 pi. And take a look at that graph. Okay, can you really even see any action going on out on the edges of 10 pi to 10 pi? It almost even disappears when you just at 4 pi to 4 pi. You can kind of barely see at 4 pi to 4 pi that it's hovering right there, and then it has its peak, and then it comes out again. We call this an oscillating graph. What the graph is doing is it's oscillating around the axis. It's like barely above, barely below, barely above, barely below, barely above, barely below. It's just oscillating around. It's not asymptotic, because an asymptote never does what? Never touches. This thing is touching the x-axis a lot, but barely. It's barely above, barely below, barely above, barely below. So we say it's going 0 plus, and then it's going 0 minus, and then it's 0 plus, and then it's 0 minus. But what's the limit? If it's 0 plus and 0 minus over and over and over again, what's the limit? 0. Okay, the limit is 0. Okay, so we come back to this, and we make our conjecture. And the limit is 0. The best way I can recommend that you remember and memorize these is to have an idea, an understanding of what the graph is doing. If you can picture it in your head, you're like, okay, when I'm in the middle, the limit is like the amplitude. It's that A value. When I'm on the edges, the limit's always going to be 0 because it's oscillating above and below the x-axis. So to have, these are two things you have to memorize. But you can always fall back on your understanding that the graph is doing this until it gets to the center, and then it has a peak. Whoops. And then an open circle, and then it decreases the rest of the way out. The greater the A, the greater the peak. But no matter what, on the edges, out here, the limit as x approaches positive infinity of sine of x over x, that's always going to equal 0. And out on the other end, on the left side, as the limit approaches negative infinity of sine of x over x, that is also going to always be 0. And in the middle, right here, the limit as x approaches 0 of sine of any ax, any amplitude x, will always be a. So those three limits, for you to have that good understanding of what that is, and that's going to help you then do some problems. Okay. Now, some people ask the follow-up question, well, what about cosine? Does cosine have stuff like that that we got to worry about? Well, what can you do with 0 for cosine? You can just drop it right in, okay? Because at 0, you can just plug 0 right into cosine. You don't have to worry about that. Okay, so let's try some examples and see how this is going to work. All right, what is the limit as x approaches 0 of tan x over x? Well, we're going to have to do a replacement of tan. We know tan is equal to sine of x over cosine of x, which is also over x now. So you're replacing using the identity. Now you're going to do some legal rearranging of things. I want to have sine of x. So instead of having sine of x over cosine of x over x, I'm going to write it like this: sine of x over cos of x and 1 over x. I'm going to do that. Totally legal, multiplying by the reciprocal. Furthermore, I'm going to do another legal thing. What should I do with the denominators? Not equal. Switch them. Switch the order. It's multiplication, right? So it doesn't matter which one comes first, so put the x under here and the cos x over there. That's still totally legal. Okay, you multiplied by reciprocal, which is legal. You've split this up, which is legal. And your final legal move can be to split it up one more time into two separate limits. And now that you have two separate limits, the front limit is one that you've memorized. So what is the answer to the value of the front limit, the first limit? We just proved it and we just memorized it. It's 1. And then what about the limit to the back? Okay, you can plug 0 directly into that and not have a problem. And then what do you get? You also get 1. So the answer to this is 1. Okay, how about this? It's all in the algebra first, as much algebra as you can do until you get to either sine of x over x or sine of ax over x. All right, how about this? What is the limit of the sine of 2x over the sine of 3x? How do we approach that? Well, we don't want the sine of 2x to be over the sine of 3x. What do we want the sine of 2x to be over? Just plain x. We would like, because that's what the rule is. Sine of ax over x. So do this. Break it up. I would really, really, really like there to be an x here. But if I'm going to put an x down in the denominator, what else do I have to do? I got to put an x in the numerator, because whatever I do to the denominator, I have to do to the numerator. Now I can break this up. And so now I can have the sine of 2x over x broken up from the separate limit of x over sine 3x. And what's the limit of the first one? Sine of ax over x. What is it? What's the a? 2. And then the other one, even though it's upside down, still works. What's the limit of the other one? 3. Or 1 over 3, excuse me. 1 over 3, because it's upside down. So the answer? 2/3. All right, go have fun at the pep rally.